So hello there, you are on Victali, and today we are going to solve four more problems. Sorry, this is the first four problems from fluid mechanics. We got some four very much good questions selected from various books. Let's dive into the questions. Question number one. An ice cube floats on water. Describe qualitatively the changes in the height of the fluid level when the ice melts in the three following cases. So the first case is a metal bead is embedded inside the ice cube. In the second case is a solid whose density is less than that of water is embedded. And the third case is the ice cube traps oil which is immiscible with water. So let's first understand the concept of this question. First thing is ice is a solid, right? But the density of ice is less than that of water. That's a major point that I have to say in this particular question. So ice floats on water. This is because of the crystalline nature of the ice structure. If you put ice in this particular water, it will slowly convert into water because of melting, right? So what happens when nothing is there? Let's mark it as case 0. If you see the volume of this particular ice, let's suppose it's V1. Let me write it somewhere. Volume of ice is Vi, okay, and volume of the water formed by this ice is V water, let's suppose. Now if this ice is floating in this, the buoyant force is nothing but how we calculate the buoyant force, or is nothing but the weight of the water displaced. So the weight of the water displaced must be equal to the weight of this ice. So mass, the weight of this ice is nothing but density of ice into volume of ice into acceleration due to gravity, which is equal to, simply just we are equating the mass of the water and this ice, okay, and density of water into volume displaced. So volume displaced is nothing but Vi into rho I by rho W, where rho I is less than rho W, so it's less than 1. So we can directly conclude Vi is greater than Vd. That is, the volume of this ice block is greater than the volume of the water which rised. The same volume of water will get raised when this whole ice block completely melts, because the mass is constant, right? So it obeys the same equation. So what volume is displaced by this particular ice block is what the same volume of water it will become when it melts. Simple, right? Let me repeat again. If this particular ice block we are putting it into a container having water, there will be a displacement of V volume of water. Okay. Now this ice block melts, right? When it melts, it produces the same V volume of water. That's the concept I am trying to explain here. So in the first case, what we have is a metal bead is embedded inside the ice cube. Usually metals have more density than water. So let's analyze the final and initial situation. Uh, Final situation, metal completely submerged. It goes to the down, right? And ice becomes water. Let's suppose metal plus ice is initially floating, right? So this metal guy weight is balanced by V1 volume of water, and this ice weight is managed by V2 volume of water. That is, V1 plus V2 is still water is there. Okay, we have a still water over here. From this, what happens is, let me draw properly. Still water is there. If I put this particular metal plus ice system, some amount of water gets displaced, right? That some amount is V1 plus V2. That's what V1 plus V2 that I have mentioned here. Now what happens? Ice melts and this metal goes down. In the final case, what happens? This V2 remains same. if you see V2 remains same. Why? Because this volume of water went up is given by the ice. So V2 remains same. That I have explained previously. And this V1 won't be same because this metal weight is balanced by water of larger volume than the metal because the density is different. See, that I have explained mathematically downwards. Let me explain. So if you see here, this V1 is greater than the volume of the metal ball. So automatically what happens? Initially, when the system is floating, we have V1 plus V2, and when the process is completed, we have V2 plus a volume V which is less than V1, where this V is the volume of the metal ball. So it's comparatively less. So water level should fall down. Okay, that's why I have written level falls. Let me explain mathematically too. So V initial is nothing but this whole system mass divided by the density of water. So we are just equating the weight based on the buoyancy. So in final case, what happens is the volume of the metal will also the volume of metal times the volume of water will rise. Also, this volume of ice will convert into volume of water. So mi by rho w plus by rho m. So if you see, compare the two equations. If you just see the denominator is different over here for mass of the metal. Here we know that the density of metal is greater than the density of water. So automatically we can say the volume at the final case is less than the initial case, so the water level falls. If you see in the second case, some part of solid is submerged because the solid has less density when compared to water. So it actually floats and the ice becomes water. Buoyancy is for solid plus ice thing, right? The solid occupies V1 volume and ice occupies V2 volume. Now, if you see in the final case, the same ice will become as V2 volume, no issues. The solid requires the same V1 volume because anyway it's going to float, right? So the level remains same. If you want to verify it mathematically too, you can just substitute V initial is same. Here I would write Vs, Ms, and this becomes the V final, where the same equation is there. So V initial is equal to V final, so the level remains same. In the third case, if you see, what happens to the oil? The oil will form a layer on the top surface of water and the ice will become the water. Okay. Now, initially the oil plus ice system is there where oil occupies V1 volume and ice occupies V2 volume. If you see finally, the the same V2 volume will be there. We have to just consider this V1 volume throughout all the cases. Okay, if they give any of the material, you can just consider this V1 volume. If you see, initially the ice part is doing this V1 volume. Now, in the next case, what happens is the V1 volume will become the same, that is m naught by rho naught. So, which is the volume of the oil because the oil will occupy the top surface, right? So, this top surface oil volume will also be added. So, this is volume of oil, which is m naught by rho naught plus the volume of the ice which converted into water. So which is mi by rho w. That's it. So if you see here, and the initial case we have, this is the initial case, right? So mi plus mo by rho w. If you see, rho naught is less than rho w. So this v, that is v final, is greater than the v initial. So water level rises. So let's go to question number 2. A circular hole of radius r at the bottom of a tank of water with density rho, the lid is open, is sealed by a sphere of radius capital R, which is greater than the small r and mass m. The water level in the tank is reduced to a certain height h, at which point the ball starts to rise out of the hole. Determine h while assuming that the water level in the tank is still above the top of the ball at the juncture where it just begins to rise. So if you see, this question is much easier, which can be easily solved with intuition. In the previous question, yeah, to develop that kind of intuition, it takes time. So just if you just see the solution, it won't be enough for the previous question. Just try to understand it. If intuition doesn't work, try using the mathematical proofs that I have used too. Okay. Now, if you see, determine H while assuming that the water level in this tank is still above the top of the ball at the juncture where it just begins to rise. When it just begins to rise, it's kind of a equilibrium state. So the force which is pulling it up and pushing it down must be equal. Which forces are pushing it up? The buoyancy and the pressure at the bottom of the sphere. This P naught is also pushing it up. And which forces are pushing it down? The weight and the water pressure on the top of the sphere. That's it, right? Now, if you see, this particular cross section is outside the container. The remaining part is inside the container. Now, let's define what is the upward forces, buoyancy. So, this buoyancy is nothing but rho g into V, right? Where V is the volume of this particular solid in this liquid, right? The buoyant force is the weight of the particle immersed in the liquid. Okay. Now rho naught pi into r square. Now if you see, sorry, this is p naught into pi r square, where p naught is the pressure over this area. I'm just considering the circular. If I see from the top view or the bottom view, I can see a circle, right? Where the sphere closes. That is the circular hole. I'm just equating the forces along this hole. Okay. You see here, this pressure P naught will be acting in all this kind of directions, where the net will be something over this direction, which is P naught into pi r square. That is what I have written here. You may think that the surface is curved, right? You may see all forces are in this direction. If you see here, the net force will be in this direction of this cross sectional area. That is not P naught into pi r square plus rho g into V, where V is the volume inside the liquid. Now, what is the downward force? Mg, that is weight, and water pressure. I'm just seeing this surface, right? So it's nothing but P naught plus P, where P is nothing but rho gh, right? The pressure at this particular point is P naught plus rho gh into the same area, pi r square. So we need V, right? We have all these things. We just need the H, that is the final answer. Okay. But we need V, which we have assumed. So it's just simple. We are going to integrate it. Okay. How are you going to integrate it? That's the question. Now, in order to integrate a volume, you need an area element and a thickness element. Okay, let's suppose the thickness is dx, or this is dy in the sense. I'm just taking y, and the radius at that particular point is x. So pi x square dy is nothing but the volume of this particular small element. If I integrate it, integral pi x square dy is gives you the total volume of the particular substance with proper limits. Okay, now the same concept I'm just applying here, where if you see pi into x square dy, where I have to put limits for y, right? So the y starts from here, right? Because this part is outside. So this length is under root r square minus r square, small r square, by Pythagoras theorem to capital R in the positive direction, positive y direction. So if I integrate it, I get pi by 3 into 2r cube plus 2r square plus r square into the whole of under root r square minus small r square. So this is the value of phi, which is the final thing. If you integrate it, it gets much easier. First thing, in order to link between x square and y, I'll say this. This is something r remains same at any point. Okay. And this is y, and x is here. So if you see, x square plus y square is always r square. So you have to substitute this over here, and the processes takes time. I don't want to waste your time here. So I'm just directly putting the answer. This is pi by 3 into 2r cube plus 2r square plus small r square under root r square minus small r square. This is the value of V. And if you substitute that particular value by equating these two equations, we get H is V by pi r square minus M by rho pi r square. That's it. We get the answer for this particular question. This question is much easier when compared to that question. The main idea you need to know in this question is you have to equate the forces along this particular the circular surface face, right? That makes the question much easier. Else you have to integrate the upward force and downward to force too. That takes much of your time. So let's go to question number 3. An open cylindrical container of height h naught and cross sectional area a1 is initially filled with water. There is a tap at the bottom of the container with cross sectional area a2 and negligible height. Assuming energy conserving flow, find the height of the water level h of t as a function of time. This is another a bit easy question. The first thing is, let me mark the pressure. So which is P naught here and P naught here at the exit and the entry too. Now rate of flow is Q, which is dV by dt. We know this. I'm just writing it to make you remember the term. Now what are they asking? Rate of change of height. If you see, the rate of change of height is U. That's it, right? It's actually U. Now this U is not given in this particular question. And V I have assumed, and U is what we have to find U as a function of time. Okay, that is the rate of change of height. Then if you integrate, you get h of t. So a1u is nothing but a2v, which is q. I'm just conserving the mass. The total amount of water entering is equal to total amount of water leaving. So from this I can write v is a1u by a2. Now I will write Bernoulli's equation for at this particular point and this particular point. Bernoulli's equation is just the conservation of energy per unit volume. What kind of energies are involved? Pressure energy, and then potential energy and kinetic energy under the ideal cases. Like there is no other work done in this particular process. So rho gh plus P naught plus half rho u square. This energy is at this particular point. So you see this particular point as a potential energy. I'm keeping this as my reference. And P naught is the atmospheric pressure over here and half rho u square. At this point, same atmospheric pressure P naught and then half rho v square. So if I simplify the terms, I get this equation, rearrange them, cancel this P naught, you get this. Now just substitute this part because V is something we assumed and U is what we need right now. So if I substitute V in terms of U, I get the final equation as this thing. Sorry, I get this particular equation. This is a simplified form of this where rho is eliminated. And if you see, I just need U right now. So I will keep U here and put all of the terms on the right hand side. So I get U is under root this thing. Now the rate of change of height is minus U. Why? The sign matters because U is positive in this direction, but the height decreases. So it should be negative. So I'm just considering dH by dt as negative of U. That is minus under root 2ga2 square h by a1 square minus a2 square. Now I have to integrate this with proper limits where h goes from h naught to h, where h naught is the initial height. Okay. And t goes from, I'm just starting the log. So it goes from 0 to t. If I integrate it, it's very much simple. I get hs under root h naught minus whole under root ga2 square by 2 into a1 square minus a2 square into t the whole square. So this is the final answer for h. This is a very much simple question. Just if you see in fluid mechanics, you need some basics of integration. Just you have to remember the basic equations like Bernoulli's equations is involved, equation of continuity is involved. That's it. And in integration, you have to mark the proper limits. If you are not using the proper limits, you may get the wrong answer. So let's go to the last question of today, which is question number 4. A massive pipe rests on a horizontal table. In this pipe, A fluid of constant density rho flows from left to right with an angle of deflection theta, as shown in the figure. Suppose that areas of the left and right ends are A1 and A2 respectively with corresponding pressures P1 and P2. Determine the force exerted on this portion of the fluid by the pipe. So this is a very much different question so far in JEE, I guess. So first thing, let's go with the path, a fundamental path. Determine the force they are asking exerted on the pipe. So we know the velocities and mass, right? So how will we ring with that force? The basic definition of force is not ma, it's rate of change of momentum. So in order to link this, we have rate of change of momentum is nothing but m dv by dt. Now v is the volume, m can be written as density into area into some length into dv by dt. Then I can replace v is constant, so density into area into dl by dt. That many variations we can be formed. Okay, so q is nothing but volume flow rate. So that area into length, I'm just writing it as volume. So rho q into dt is nothing but dm. Volume flow rate is nothing but dv by dt. So dv by dt into rho is nothing but dm by dt. Into dt I get dm. That's it. This is the main equation. I'm just have to write the initially I'm just assuming the speed as u, and in the final case I'm just assuming the v in this particular direction. So that I have written as u to v. Now if you see the net change, the overall total force from this to this in x direction, we have rho q into. Now first, how am I writing this way? I will just explain it. If you see, this is correct, right? Now we want dm by dt into v or m into delta v. So rho q by t. Rho q is nothing but m by t, and delta v is nothing but the change in velocity. That is what I am going to write here. So initially it's u and finally it's v in this direction and cos theta in x. So rho q into v cos theta minus u. This is the total force in x direction. Similarly, if you write the total force in y direction, this has zero component in y direction and this has a component which is rho q into v sine theta. Simple, right? Now our mission is to eliminate q and rho because sorry, not rho, q, and our mission is to eliminate u, v, and q. Rho is given, v and u, q is what we assume. So in order to eliminate q, we have the equation of continuity that I have written over here. So which is q is nothing but a1u equal to a to v, but that too has u and v. So I need to find some more. The next equation is Bernoulli's equation where you have to eliminate u, v, and q. It's combined thing. These two get combined to form what we wanted. Something, this question seemed to be magical actually. So the pressure at this point is P1. So P1 plus this kinetic energy at this point equal to P2 plus kinetic energy at that point. And the potential energy is zero because everything is happening in the same horizontal surface. There is a table. So rho, and this writing as rho is this thing. And let me keep it this part here. And I have this thing over here, which is q is nothing but a1u, which is equal to a to v. What I'm going to do is I'm going to replace u with q by a1 and v with q by a2. I'm just doing it here. And if I do it here, I get q square, right? That q square I just transferred it to the LHS. So rho q square is nothing but twice of p2 minus p1 whole divided by 1 by a1 square minus 1 by a2 square. Simple, I'm just replacing u and v in terms of q. I'm just making it into a single variable using these two equations. Okay. Now, if you see, if I substitute the same transformation, that is u I'm replacing with q by a1 and v I'm replacing with q by a2 in this particular equation, things get changed. So you see, if I change that way, I get f total in x direction is rho q square times cos theta by a2 minus 1 by a1, and f total in y direction is rho q square times sin theta by a2. So we get rho q square. That is what we found, right? So it's very much magical. So if you substitute directly over here, you get the final answer. So I'm just leaving the calculation part to you. You just try it. And the thing is, the question is not over here. Most of the people will think the question is not over and they will mark this as the answer. But what happens is, we just found out the total force. We see the total force is due to the water pressure as well as the wall. But they are asking the force exerted by the pipe or the wall of the pipe. So I'm just going to find force due to the wall is F total minus force due to water pressure. So how are we going to know what is the force due to water pressure? That's much confusing, right? It's simple, P1 into A. That's P1A is in this direction and P1A for this is in this direction. Just take the components for this P1A into cos theta in this direction and P1A into sin theta this direction. Sorry, this is P2A2 into cos theta and this is P2A2 into sin theta and this is P1A. So if I write it, force due to the water pressure in x direction is P1A1 minus P2A2 cos theta, and force due to water pressure in y direction is minus P2A2 sin theta. Just put these things in this particular equation and you will get the final force equation, right? This question is a bit of basic concept, right? You can just use the basic concepts of force, that is change of momentum, and you can do it. But it has more number of variables, slightly confusing. If you miss a single term, you won't get the exact answer. So be careful while attempting these kind of questions. So the first question of today seems to be a bit of confusing. You will find out the intuition and logic for that question soon when you practice it again and again. And thank you for watching this video. Do comment the doubts from this video. We are here to solve it. Stay tuned.